Angle of elevation, introduction. Welcome, everyone. Today, we are diving into a very practical part of trigonometry. Now, when we study trigonometry, specifically when we are dealing with problems involving heights and distances, we often run into situations where we need to find the height of something very tall, like a building or a tower, without actually climbing it with a measuring tape. It would be quite difficult, wouldn't it? To solve these types of problems, we use a very important concept called the angle of elevation. This concept is our bridge. It allows us to take a real-world visual observation, basically what you see when you look up at something, and translate that into a mathematical right-angled triangle that we can actually solve using formulas. Over the next few slides, I will show you exactly how to visualize this and how to perform the calculations. Understanding the concept. If you look at the first point, the angle of elevation is specifically the angle formed between two lines. First, the observer's horizontal line of sight, and second, the line of sight directed upward toward an object located above the observer. To make sure this concept is crystal clear, before we move on to visualizing it in the next slide, let's break it down into three fundamental components. First, we have the horizontal level. I want you to imagine a straight, imaginary line extending directly from the observer's eye, running perfectly parallel to the ground. This serves as our flat, horizontal reference line. Second, there is the line of sight. This is the imaginary path or line that connects the observer's eye directly to the specific point being viewed, such as the very top of a building or a tower. And finally, we have the angle of elevation itself. This is the actual angle created at the moment the observer tilts their eyes upward from that horizontal reference line to follow the line of sight toward the object. Essentially, it is the opening or the amount of upward tilt from the horizontal position. Now that we've introduced the purpose of trigonometry in measuring heights, let's dive deeper into the actual definition. Step-by-step visualization. Now that we have defined the components of the angle of elevation in the previous slide, let's bring this concept to life with a step-by-step visualization. I want you to imagine yourself standing right here on the ground, looking up at the top of a very tall building. First, let's consider step 1. Recognize that your eyes are positioned at a certain height from the ground. This is our starting point. Moving to step 2, imagine you are looking straight ahead, perfectly level with the horizon. This straight path represents your horizontal line of sight, which we discussed earlier as our reference line. Next, in step 3, to see the top of that building, you have to tilt your head upwards. This movement creates a new line of sight, connecting your eyes to the top of the structure. Finally, in step 4, the actual amount that you tilted your head upward, measured from that original horizontal position, is exactly what we call the angle of elevation. Keep this mental image in mind, because in the next slide, we are going to apply this exact visualization to a concrete mathematical problem involving a tower. Real-world example, calculating the height of a Minar. Now that we understand the theory behind the angle of elevation, let's put it into practice with a concrete example. Imagine a scenario where a student is standing at a specific point on the ground, which we will label as point P. From this position, the student looks up at the top of a Minar, or a tower, and notices that the angle of elevation is 30 degrees. We also know that the student is standing at a distance of 10 meters away from the base, or the foot, of this Minar. Our mathematical goal here is to determine the total height of the Minar. In the next slide, we will break this down step by step to see how we can use trigonometry to find our answer. Step-by-step mathematical breakdown. First, let's look at step 1, where we identify exactly what information we have been given. From our example, we know the distance from the observer to the foot of the Minar, which acts as our adjacent side, is 10 meters. We also have our angle of elevation, theta, which is 30 degrees. Finally, we have our unknown variable, the height of the Minar, which we will represent as h, also known as the opposite side. Next, in step 2, we need to represent this entire scenario as a right-angled triangle so we can apply our trigonometry rules. Let's label our triangle. We will represent the vertical Minar as the line segment AB. The horizontal distance from the foot of the Minar to the observer will be the line segment BP. The line of sight, which we discussed in the previous slides, will be our hypotenuse, the line segment AP. Looking at our triangle now, we can clearly see that angle of PB is 30 degrees. Our base BP is 10 meters, and our height, or perpendicular of B, is h. Finally, in step 3, we need to decide which trigonometric ratio is the best tool for the job. Take a look at what we have and what we need. We already know the length of the adjacent side, and our goal is to find the height, which is the opposite side. Since we are dealing with the relationship between the opposite and the adjacent sides, the tangent ratio is our perfect choice. As a reminder, tangent theta equals the opposite side divided by the adjacent side. Now that we have visualized the scenario in our minds, let's move into the actual mathematical breakdown. This is where we translate that real-world picture into numbers and symbols we can work with. In the next slide, we will plug our specific numbers into this formula to solve for the height. Step-by-step mathematical breakdown continued. Step 4 is simply a matter of substitution. We take the values we identified in the previous slide, our angle of 30 degrees and our adjacent distance of 10 meters, and plug them directly into our formula. This gives us tangent of 30 degrees equals h over 10. Next, we move to step 5, where we solve for h. To do this, we need to use the exact value for the tangent of 30 degrees, which we know is 1 over the square root of 3. When we substitute this into our equation, we have 1 over the square root of 3 equals h over 10. To isolate h, we multiply both sides by 10, which leaves us with h equals 10 over the square root of 3 meters. Now, in mathematics, we prefer not to leave a square root in the denominator. So, by rationalizing the denominator, which means multiplying both the top and the bottom by the square root of 3, we arrive at our final, polished answer. H equals 10 times the square root of 3, all over 3 meters. Now that we have identified our trigonometric ratio as tangent, let's move into the final stages of our calculation. This value represents the height of the Minar. In the next slide, we will summarize the key concepts we've learned today. Key takeaways. First, it is crucial to remember that the angle of elevation is always measured upward from the horizontal line. As we saw in our visualization earlier, you start with your eyes looking straight ahead, and any upward tilt from that level creates the angle. Second, this concept is specifically used when the object you are viewing is positioned higher than your eye level. If you were looking down at something, we would be dealing with a different concept entirely. Third, when you are translating these real-world scenarios into a right-angled triangle on your paper, the angle of elevation is typically located at the observer's position. That is, at the vertex where the base meets the line of sight. Finally, as we demonstrated in our step-by-step breakdown, the most common trigonometric ratio you will use is tangent theta. This is because, in most height and distance problems, we are working with the relationship between the height, which is our opposite side, and the distance from the object, which is our adjacent side. Now that we have worked through the calculation for the height of the Minar, let's pause and summarize the key takeaways from today's lesson to ensure you have a solid foundation. Before we move on to some common pitfalls to watch out for, make sure you feel comfortable with these core principles. Common mistakes to avoid. Now, before we wrap up our lesson, I want to touch upon some common pitfalls. Even if you understand the concept of the angle of elevation, it is very easy to make small errors that can lead to the wrong answer. Let's look at 3 specific mistakes to avoid. First, be careful not to measure from the vertical. A very common error is measuring the angle between your line of sight and the vertical object, like the tower we used in our example. Remember what we discussed in the earlier slides. The angle of elevation is always measured upward from the horizontal line of sight, not from the object itself. Second, watch out for incorrect ratio selection. In our calculation for the Minar, we used the tangent ratio because we were working with the height and the distance on the ground. However, students often mistakenly use sine or cosine. To avoid this, always look at your triangle and identify which sides you have. Ask yourself, am I dealing with the hypotenuse, which is that slanted line, or am I dealing with the base and the height? This will tell you whether you need tangent, sine, or cosine. Finally, don't ignore the observer's height. While our example assumed the student was looking from ground level, in more advanced problems, the problem might state that the observer's eyes are at a certain height above the ground. If that happens, the height you calculate using trigonometry is only the height from the eye level upward. To find the total height of the object, you must remember to add the observer's own height to your final result. Keep these points in mind, and you'll be able to tackle even the most complex trigonometry problems with confidence.